Greetings, friends of astrobiology. Welcome to a brand new episode of Ask an Astrobiologist, a show where we celebrate science and celebrate scientists. My name is Sanjoy, and this program is made possible by contributions from the NASA Astrobiology program and the non-profit Blue Marble Space. Today, we're extremely lucky to welcome Dr. Jennifer Glass, who is a professor of biogeochemistry at the Georgia Institute of Technology, as our guest. But first, it's your favorite monthly background quiz. Last month, we had the picture of a beautiful site. Mike, if you can put it up for a few seconds. It was, of course, the beautiful Mono Lake, which is east of Yosemite National Park in California in the United States. And the person who got it right is Marianne Denton. Marianne, congratulations. You'll be winning the full set of the Ask an Astrobiologist, or rather the astrobiology graphic novels, as well as some NASA stickers. Congratulations. Next month, your job is to guess what is behind me. It's a little bit harder this time, but enjoy it. Mono Lake is a fantastic lake in California. It's very alkaline and had these beautiful towers of calcium carbonate called tufas, and they are formed and they testify to the presence of underwater springs who deliver calcium, which react chemically with the carbonate that's in the water to form those towers. And so when the lake levels fell, those revealed those beautiful towers. So if you get a chance to head down to Mono Lake, I highly recommend it. It is really a feast for the eyes. I have also some other exciting news. Together with Ask an Astrobiologist and SIGINET, we welcome Dr. Graham Lau, who is in the chat room right now. Dr. Lau is an astrobiologist and a research scientist at the Blue Marble Space Institute of Science, and he will be co-hosting Ask an Astrobiologist with me. So we'll be alternating more or less who presents the show, and it's going to be a wonderful experience to welcome him on board. But enough about us. This program is meant to focus on a fantastic scientist of astrobiology, and with that we have Dr. Jennifer Glass with us today. Jennifer, how are you today?
Great.
Wonderful.
It's a beautiful day in Atlanta. It's
a little balmy, I hear. You are a professor of biogeochemistry at the Georgia Institute of Technology in the city of Atlanta in America. And could you tell us what is biogeochemistry to begin with?
Yes. Well, as you know, we like to, in astrobiology, sometimes it's kind of like in German, string these words together. And so obviously it's biogeochemistry, right, is the kind of intermingling of biology and geology and chemistry, and also physics is needed in there as well. So it's essentially kind of all sciences merged together, and like astrobiology is as well. So sometimes I call myself an astrobiologist, sometimes a biogeochemist, sometimes geomicrobiologist. It's hard to kind of come up with a single name because it's such an interdisciplinary field. But basically what biogeochemists tend to be interested in is thinking about how chemical elements, how the elements on the periodic table cycle through Earth systems, and also, especially in astrobiology, we like to think about other planetary systems as well. And that often comes down to microbial reactions, because the microbes are actually who can really catalyze a lot of this chemistry much faster than the abiotic processes. And so that's the connection into microbiology as well.
So you look at microbes, you look at gases, you think about the atmosphere, you think about rocks. You're a true astrobiologist, right? You can't do modern astrobiology by being focused on a particular discipline. Even most science today, you cannot do that.
Astrobiologist, right?
One could say that, indeed. So presumably you weren't a 6-year-old looking at a rock and thinking, I want to become a biogeochemist. But could you tell us a story perhaps when you were a kid, or what triggered this interest in science, and discuss your career path and how to become a biogeochemist interested in astrobiology?
Well, I was really fortunate to grow up in the beautiful state where Dr. Sam and I also happen to have gone to school at the same time. He is a graduate student and myself as an undergraduate at University of Washington. And I grew up in Olympia, Washington, and which is, for those of you who haven't visited the Pacific Northwest of the United States before, it's a beautiful place. It's there's volcanoes, there's a temperate rainforest on the Olympic Peninsula. It's kind of a marvelous wonderland of biogeochemistry and biodiversity. And I think that I was very fortunate to grow up in a place that I think naturally just gets you thinking about Earth processes. And I actually did my first year of college at UC Santa Cruz. And I know maybe we'll talk later about mentors and how important they are, because there were some mentors there that really encouraged me and drew me into actually oceanography. And then I basically, all through undergrad, it was really hard for me to decide what to major in because I was interested in everything. But I was interested in all natural sciences, basically, and biology and chemistry. But I really liked the applied side of it. And so that's how I came to geosciences. And I've always been in geosciences ever since. And the beauty of geosciences is that they let us, it's pretty interdisciplinary, as well as increasingly really all of science is. We have to be more and more interdisciplinary because at the intersections is really where the interesting problems and answers are. So I've been fortunate to be able to do this very interdisciplinary science in geoscience departments ever since I was in college.
Wonderful. So you got your undergraduate degree in geology, and then you moved to Arizona State University for your doctorate. Mm-hmm. How was that transition?
Yeah, well, I was fortunate to have wonderful mentors at University of Washington, and some of whom we share, talk about. And there was a wonderful astrobiology program as well. And so that was where I really got interested originally in astrobiology, and that was how I found out about Arizona State and some of the really exciting research going on there. So it was, well, the transition to graduate school is a challenging one, I think, for a lot of people. And it was challenging for me as well, especially going from, like you said, the geosciences and then trying to learn basically this whole new world of microbiology and also a fair bit of biochemistry as well. And I'm still in the process of doing that. So
you never stop learning. That's the beauty of the scientific discipline.
Later, yeah, that's a good thing. Exactly. I'll never be done, transitioning around between those. And I've just been fortunate to be able to do that in this community and to be able to work on quite a number of different problems. That's just naturally what I like to do. I get excited about a lot of different things. I try to focus on something long enough to finish it, at least get some papers out. But we can talk more about that, about what I'm excited about lately.
Yeah, absolutely. Your enthusiasm is like oozing out of the screen that I have in front of me. It's wonderful. But let's talk about mentors a little bit. Because the scientific path through school is not the easiest path one can choose to get a degree in and get multiple degrees in. And people might think that they're not smart enough, not good enough to do this career, but of course it's incorrect. All of us who have gone through the school in the sciences have benefited from mentors. And I'm wondering if you could share some stories about the people and perhaps even give them a little shout out who've encouraged you over the years.
Yes, absolutely. And there's more than I can possibly talk about here, but I want to go all the way back to K through 12, because it's really, I think, especially in the States, which is what I can speak to, and in the public school systems in the States, our teachers work so amazingly hard for very little money. And I was so blessed to have such amazing science teachers in school, because it was really my middle school science teachers, who were both women, actually, and especially really both of them, but my 7th grade science teacher, Carol Serdar, and then my 8th grade science teacher, Maddie Martin. They both really directed me, Carol very much on the natural sciences side, and then Ms. Martin, I'll call her, more on the track for going forward. I don't think I would be where I am without those two amazing women. And after that, I'll just name 4 amazing women, and then I can give many, probably hundreds more. But then my first year of college, actually, like I said, I I wasn't sure what I wanted to do. I was very much interested in saving the planet. That's what I wanted to do. I wanted to save the planet. Just the, little thing. So, so I went to UC Santa Cruz because they have a really good environmental science program. And amazingly, the summer before I started at UC Santa Cruz, I got an email out of the blue from a faculty member who is Professor Ana Cristina Ravello at UC Santa Cruz, saying, I saw your undergraduate application and I was really impressed, and would you like to come work in my lab?
Wow.
And that was, you can imagine how honored.
Absolutely.
And so, the year I spent there, I ended up transferring to University of Washington after that. But the year I spent in her lab at UC Santa Cruz, that absolutely made me, was huge in terms of getting me interested in oceanography, because her group works on paleoceanography. Just being in a lab group for the first time as a freshman in college and just kind of seeing the inside track there. And I remember I was working with her graduate student who's now at Stanford. There was also, I was supposed to be talking about mentors. And then I'll just move on from there and jump forward a little bit, because I want to give a big shout out to Felisa Wolf-Simon, who actually was my mentor my first year at Ariel Anbar's lab at Arizona State University. And Felisa was absolutely the best mentor I think I can say I've ever had. I don't know if she's watching this, but
Hopefully.
I want to say thank you, Felisa, because I'm going to choke up a little bit with that, because we had, she was just amazing to me, and she really taught me what I know about, definitely growing cyanobacteria, that's for sure. We grew a lot of cyanobacteria in that lab in the basement of Phoenix, getting liquid nitrogen in the 120 degrees. Took a while. So I want to, say a huge thank you to Felisa.
So this illustrates that the scientific career is an emotional one as well, which is important to grow in that facet. So after your PhD at Arizona State, you did a postdoc at the California Institute of Technology, and now you have your own lab at Georgia Institute of Technology. And I guess the title of your lab is Mars, Methane, and Metals, this wonderful alliteration in M's. Tell us about what your lab does.
I don't know if Mars is in there. I'm
it's
not.
Oh.
But
There's 3 M's.
It's methane, microbes, and metals, I think.
Microbes.
But we switch in and out, so you're right. Maybe I don't know if I can call myself enough of a Mars person. I've been trying to beef up on my Mars, but you're right. Yes, metals, methane, and microbes. Yeah. I would do more than that now, but that was a fun alliteration that I came up with. Actually, I think I had that idea at AppGradCon in Bozeman, actually. So it all comes back to.
I think I remember that too.
So I'm sorry. What was your question?
What does your alliterative lab do?
What do we do? Okay. Right. And so we're interested in thinking about the cycling through space and time of mostly two greenhouse gases. CO2, a lot of people work on, so we work on the kind of a little bit more neglected ones that are methane and nitrous oxide, the second and third most important greenhouse gases after CO2. And so we're really interested in how microbes cycle those greenhouse gases, but also how interactions between chemistry and the microbes can be really important for those gases.
So methane and nitrous oxide, laughing gas as it's known, were really important to warm the ancient Earth, several billion years ago. At that time, as we know, the sun was fainter, so we needed those greenhouse gases to keep the planet warm. And so right now, those gases are not so present in our atmosphere, so the wonderful discipline of atmospheric evolution is probably what you're interested in as well, and particularly that transition around 2.4 billion years ago when the Earth transitioned to have oxygen in the atmosphere. And And that changed quite a bit, the composition of the air, as well as the effects on microbes. So when we think about the evolution of the air, we have to think about the evolution of the land and what microbes contributed, hence the biogeochemistry, I think.
Exactly. Yeah, so go ahead.
Oh, I was going to talk about one of your papers that's coming out very soon in Geobiology, talking about a new interpretation, a new explanation for this laughing gas in the atmosphere of Earth several billion years ago.
Yes, and the first author is Chloe Stanton, who spent 4 years in my lab as an undergraduate here in Earth and Atmospheric Sciences at Georgia Tech, and then now has gone on to work at Penn State in their astrobiology group. So I'm really, really proud of her.
Congratulations, Chloe.
And this is also, this study is funded by NASA Astrobiology, and specifically the Alternative Earths team that's based out of UC Riverside, and we also have a node here at Georgia Tech. So basically, we were interested, and this kind of dates back, my interest in nitrogen actually dates back to essentially when I first met Sanjoy, which was, I think, 2004-ish or so, thereabouts. Maybe 15 years ago, I don't know, something like that. Yeah, it does, yeah. And so at University of Washington, actually, and we had a shared mentor, Roger Buick, who maybe, many of you know, and wonderful mentor. And so this is originally, actually, I think this hypothesis, as far as I can tell, of this laughing gas atmosphere was really originated with Roger Buick, and he came up with this idea that maybe laughing gas, which is quite a potent greenhouse gas, was more abundant in this middle period of Earth history. And so we're really focused on that same topic, and in terms of, which is what a lot of my lab is kind of focused on, is thinking, how would a really metal-rich ocean, specifically iron, but also manganese, we know that the ocean, it could have had up to millimolar levels, maybe a little lower. There's a lot of debate about that. But it was loaded with ferrous iron, soluble ferrous iron, and there was a lot of rapid cycling through the Ferris wheel of redox cycling. So how would that iron-rich ocean have affected the nitrogen cycle? And actually, it's long been known in the soil literature that if you react oxidized nitrogen species like nitrite and nitric oxide, if there's a lot of iron around, they react and they make nitrous oxide, actually, chemically. This doesn't, and it's very quick, and so that's been long known. And we basically did experiments in the lab to show that you can very rapidly get a lot of conversion to nitrous oxide just from that iron chemistry, essentially. And so that's kind of our new proposed mechanism for a potential laughing gas Buick atmosphere, with implications as well that I can talk about if you're interested for the evolution of aerobic respiration, what we're doing right now.
Fascinating. Yeah, I mean, this whole amount or abundance of metals in the ocean is important because prior to the Earth having oxygen in the atmosphere, the ocean also didn't have any oxygen inside it, and so the iron could accumulate, and as oxygen started to rise, all the iron can oxidize, which formed metals and fell down, and also the oxygen in the atmosphere kind of prevented large amounts of metal flushing down into the oceans, which changed the amount of copper, and I know nickel that you're interested in as well, and bacteria use these metals in the enzymes in their proteins they use to change the chemistry of nitrogen all the way back to N2, which is what we breathe. And copper was very important in that last step, as you were mentioning, and with a lack of copper, perhaps, it's a hypothesis, bacteria could not go from that last step, nitrous oxide, to N2. And so the atmosphere stayed at nitrous oxide, which is fascinating.
Right.
So you bring in the importance of iron in that story, which is cool.
Right, yes, and just as an alternative pathway, essentially, for how to get the nitrous oxide. Now, in terms of how the how much of that nitrous oxide the organisms could actually breathe is another question. Whether it was copper limitation that controlled it. There's actually new data kind of showing that copper has been pretty consistent. That's the latest I heard. So that's a little, questionable there. But regardless, it's very important to understand that last step, because that last step, the last two steps of denitrification merged together and became how we breathe oxygen. So that's what really has me excited lately, is thinking about the evolution of Cytochrome C oxidase, which has a huge interest, obviously. That's a super important enzyme for all us humans.
Well, tell us more about this evolution of these aerobes.
Yeah, and so...
What is an aerobe?
What's an aerobe? So an aerobe is an organism, like we are aerobes, so we are using oxygen. We're breathing oxygen, right? But there are... maybe your next question was going to be what's an anaerobe, right? So there's actually what is less well known. Of course, we've all kind of maybe heard of breathing oxygen, hopefully, but maybe not everybody knows that a lot of microorganisms can breathe all kinds of other stuff besides oxygen. So they can breathe all kinds of oxidants, and their oxidant does not have to be oxygen. And so those are called anaerobes when they're breathing not something other than oxygen.
That leads us to methane, for example, because you have some microbes that breathe carbon dioxide to reduce hydrogen to form methane, which is we find in bogs kind of on Earth. If you kind of go in a muddy bog and tap the mud and see those bubbles come out, that's typically methane. And methane is cool because it's been discovered in the atmosphere of Mars. And I know that somebody has asked a question, which reminds me to ask all of you that if you have a question, use hashtag AskAstrobio on Twitter for Dr. Glass, or write it directly on SegaNet, and we'll answer them. And so methane, you work directly with trying to understand the methane cycle as well, right?
Mm-hmm. Yeah, that's right. Yeah, and it's really exciting, the recent results back from Mars, right, to try to figure out where, and Enceladus, it seems like more, and Pluto, right? Lately, there's also Pluto. Well, these are all different. There's also methane dunes which blows my mind, on Pluto, right? So yeah, there's a lot of recent exciting methane discoveries in our solar system and probably beyond as well.
Let's talk about Mars, because it's closer to home, and we have a rover, a couple, in fact, on the surface of Mars. In particular, Curiosity on Gale Crater has an instrument that was able to detect parts per billion concentrations of methane on the surface. Now, we know that there are biological ways of creating methane, and there are geological ways of creating methane. Nonetheless, the fact that there is methane there is really exciting.
It is exciting.
And Mike, I think you showed up the picture of the cycle there of methane on Mars as we're be able to understand more and more. And I'm just wondering, what are your thoughts? Do you think it's life on Mars, Jen?
So, and I think the latest discovery, right, is that there's seasonal variation as well. It's very small quantities, right? It's orders of magnitude lower than what we have. We have almost 2 ppm. I'm gonna get that right, and then this is like 10 ppb parts. That's parts per million and parts per billion, right? So 3 orders of magnitude different. But still, the fact that there's seasonal variation really has struck people as okay. On Earth, right? Seasonal variation with CO2, that's biology. That's the Earth breathing, literally. That's respiration and photosynthesis, right? That controls those seasonal variations. And so I think those seasonal variations led a lot of people to think, could this be biologic? The thing about methane is something like 90% of the methane cycle on Earth today is biologic. So it's really amazing how biology, and specific, it's not just by all of biology, it's a specific clade of archaea, not bacteria, they're archaea, the third domain of life, who make methane on Earth. So the question is, and there's been a lot of work in our field in astrobiology doing experiments, right, about taking cultures of these archaea, obviously Earth cultures of the archaea, and growing them under these conditions that could mimic what it's like on Mars or Enceladus. And in fact, they found, some recent reports have found that some of these Earth archaea can actually live under pretty close conditions to what we find on these other planets. So it's kind of not crazy anymore to really think that maybe that could actually be like tiny trickle of little. Now, I'm not saying obviously Mars is not like a flourishing ecosystem. I think we can agree on that today. But hey, but the fact, if there even is a tiny little film somewhere, that still fundamentally would change, right, our whole view on the universe, right?
Oh, absolutely.
That's, I guess, the underlying premise. And I think a lot of, given the excitement I've seen just amongst the public, I think that a lot of us share that enthusiasm. It's just such a inspiring time. I think it's so fun to be working on something that just gets people excited, that's a positive, that's just mind-bogglingly cool, basically, how fortunate we are. So
absolutely. I think that's one of the reasons I like astrobiology so much, is because of all these philosophical repercussions about, if we do find life elsewhere, what does that mean to be human? And if we don't, what does that mean about our responsibilities of stewardship? It's very interesting. So you're primarily a terrestrial biogeochemist, but I know you're getting involved in some workshops and some groups that are discussing how to explore for life on icy worlds, and those are moons of Jupiter, like Europa.
Yes.
Wow, how did I forget that? And Enceladus, which is a moon of Saturn, of course. Could you tell us a little bit about your involvement and what are the thoughts there?
Yes. So I have an amazing colleague here at Georgia Tech who hopefully a lot of you already know about, because she's amazing, is Brittany Schmidt here, just upstairs one level. And ever since I've been here, and I also got to know Brittany a bit because we have this amazing early career astrobiology community. And so even before that, I knew her from our grad cons and things. But working with Brittany here has just been amazing because, her group is designing robots that could actually be used on Europa in the future when there's a Europa lander mission, which is in the works, right, in the future, being planned. And so they've got a plan. They've got to, go practice these things on Earth. So her group, it has built this vehicle called IceFin. I think it has a Twitter account and an Instagram account. So go search IceFin on the social media, and you'll see a bunch of amazing pictures of them down in Antarctica. So they're using under the Ross Ice Shelf as an analog for Europa, and testing their robot down there, and looking at the conditions and habitability in comparison to Europa. And so I haven't been to Antarctica yet, but I do get to play with the samples when they come back. I get to help her graduate student, Justin Lawrence, with some of the analyses. And so we'll be looking at the microbial ecology of those samples. So we're excited for that. And I was going to mention also that when I felt most like an astrobiologist was when I got to sit in on her conference call when she's organizing a paper on the planetary protection of Europa, and she's either in charge of, she's part of this community, high up in it, in charge of that. And I just thought, just the fact that I get to be sitting in on this conference call, an author on this paper, I get to be thinking about how to protect Europa from cells coming in from Earth. I mean, this is just surreal, this is literally the best job, ever. So I just can't say enough how fortunate. And that brings me to wanting to also help the next generation to become astrobiologists. As well.
I will talk about that. But we've been chatting for half an hour, so I want to open up the floor to our audience who are watching and listening. Again, if you have a question for Dr. Glass, please use hashtag AskAstrobio on Twitter or ask the questions directly on the chat on seganet.org. The first question is in regards to the methane on Mars, and it's from Michael Wong, and he's curious, how would you design a mission to be able to tell whether or not the methane is geologic or biologic?
So that is and I think that this is coming up in future missions, I imagine. And so there are so I'll probably rely on some of you for help with this question too, because I think this has been worked on, so I don't want to mislead here. But there's characteristic isotopic composition, so the ratio of carbon. So there's two different isotopes, just for those of you that I know we have a bunch of different backgrounds here, right? So the carbon, the central atom of methane, right, can be carbon 12, which is the much more abundant, or carbon 13, and the ratio of those two isotopes of carbon can be diagnostic for where the methane has come from, especially if you can also simultaneously do a measurement of the hydrogen composition as well. And so, and I believe that's already being done or in the works. I think some of that, anybody help me out on this? So that is the isotopic composition is definitely something that would be important to do. And also, I was going to mention as well something else I'm really excited about is the drilling into the subsurface to see if we can, and maybe not even drilling, maybe just doing ground penetrating radar also, to get really kind of a better understanding of the methane hydrate structures as well, because there's this hypothesis that the methane that we see, this seasonal cycle, might be coming from methane hydrates. And I'm actually very interested in the methane hydrates as an ecosystem for organisms. We are studying that in my lab right now, because there's very unique communities that live only in methane hydrates. And so if we can get, there's going to be sample return. I don't know if we'll be able to get that Mars methane hydrate back. That would be obviously the very best thing, is to drill a chunk of that and then take it all the way back to Earth and analyze the heck out of it. But we might not be able to do that in our life, although we might in our lifetime, maybe.
Fingers crossed.
That would be pretty great to be able to do some drilling, or at least get a lot better understanding of the structure of the methane hydrates on Mars.
Yeah.
If there are, but that's still controversial, I know.
The current rover on Mars is not really a life detection rover. It's a planetary environment mission. And so perhaps the next generation of missions will be focused on life detection and will include the instruments.
That's my understanding, right? That's the Mars, that's my understanding for Mars 2020, right? Is that, and forward from there, is that we're moving in that direction, right? So, but the people
I know
in the room can speak a lot more of that than I can.
Beagle 2, which was a European lander that unfortunately did not make it, had such an instrument. So we have to try again. Mars is hard, but we'll get to it. The next question, I think, is one you want to touch on as well. Luke is asking about some advice you would have for incoming students who are interested in a career in astrobiology.
Yes. Well, first of all, thank you for your interest and welcome. And we are interested in you being on board. And so, by all means, join SegaNet. This is being hosted through, so you should have easy access to the website there, and link up with a mentor, because the very most important thing, even if you're at a university that doesn't have, as far as you know, any astrobiology, let's assume that you can't really find anybody that's interested in it. Best case, there's tons of people and it's going to be easier. But let's say you don't have access to that, then you're going to need to rely much more on the internet. But you have, hopefully, the internet fairly available at your fingertips. And so get on, that's the beauty of having social media now, is that I'm always on Twitter, and so are a lot of us, and if we're not and SegaNet as well. And so get a mentor through there, to email. Now that I am I'm not through the tenure process. I'm up for tenure as we speak.
Fingers crossed.
Just put in my tenure package. So I keep saying I'm going to do it after tenure. That's what we all say, right? So I have a lot of things to do now after tenure. So I would love to do more mentoring as well. Hold me to that, Sanjoy.
I will.
So, that's the scenario if you do not already have a program. Now, on SegaNet, you can see there are a bunch of universities in the U.S. and internationally that do have programs. And so by all means, ask your professors. Some of them might be like, some people, the first time they hear astrobiology, they think, they don't quite understand what it's about. We have to teach them that it's not little green men or anything. But hopefully you can find, regardless of what you end up doing in your career, having the mentors is so essential. That's the one thing I've learned in my life, is how essential it is. So, really get, for the classes that you're really interested in, going to the office hours, asking to work in the labs if you're really interested in that group. By all means, ask to work if they have a research lab, if you could work in that research lab and get some research experience, and then that'll just kind of snowball from there. You can do summer programs, right? You can do REUs, and there's astrobiology summer programs you can apply to. So, but you need to kind of get your foot in the door. And what I want to emphasize is that foot in the door does not have to be a program at your university, because that's going to limit a lot of people from getting in the door, right? Because there's something like 20 or 30 programs. We're starting one here at Georgia Tech, but there's other places that might not. So by all means, get your foot in the door online if you don't see your university up there. Obviously, you see a lot of university of blah, 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 blah. But there are many, many, many more schools, and, we recognize that. And there's one thing I've learned about this community, this astrobiology community, is how inclusive it is, how good it is to its early career people, and how amazingly inclusive and welcoming it is. And that's something to be really, really proud of, and to really, really want to keep going. And we have amazing people to leadership in this community to thank for really fostering that. So yeah, come to SegaNet, and I'll try to mentor.
Well, I want to return the shout outs to you, Jennifer, because you are very active in promoting diversity in science and women in science. And I was wondering if you could tell us a bit more about these efforts that you're doing.
Yeah. So a lot of this had to do, honestly, I'll just be very candid, I guess, with me, a white woman, I'd say a white feminist 5 years ago, kind of moving to Atlanta and learning a lot in the process. I honestly, grew up in Olympia. It's a pretty kind of white small town. There was not much diversity in most of the programs where I was in school, and I was pretty oblivious to that. What I was more passionate was kind of feminism, but I'm going to be honest and say it was probably a pretty white feminism looking back on it, because I wasn't thinking very broadly. Like now I don't say women and minorities, I say white women, and because that's true. It's white women and minorities. Otherwise you're assuming that women are white women, and there's a lot more women than just white women. So it's basically been me trying to learn ever since I moved to Atlanta. Really trying to, first of all, learn, because I had a lot to learn, and then trying to change the system, which I rapidly learned, and learning how challenging that can be, but also, but I think it's really important for me to understand how challenging that is, and just in the process of kind of talking about how challenging it is, I think that can maybe be that can be really productive, maybe in and of itself, is talking about what the barriers are, and for me to understand what those barriers are as well. Because a lot of times maybe the barriers are hidden from those of us who, especially frankly white people, they might not see those barriers. They probably don't see those barriers. So, first of all, learning about those barriers and how to then basically rip them down.
That's part of those saving the planet efforts that you were talking about before. So I want to talk to you a little bit about those methane hydrates, because they are super interesting. Could you describe what are methane hydrates to begin with?
Oh, yes, I love methane hydrates. I've been in love with methane hydrates ever since I was at University of Washington. I actually got assigned to write a term paper on them, and I fell in love with them then, and I was determined to work on them, and I got to be 6 years later as a postdoc. I got to actually see these. So what are these? These are basically it's basically ice. It's water ice, but it's a cage of water ice encasing methane molecules, and they're packed together. So it basically looks like ice, but it's got methane in the middle. And these occur under low temperatures and high-ish pressures. So on Earth, they are in the mud on the seafloor, under the seafloor, off of continental slopes, basically. Like, you can just go right out off of the Carolinas and see them. Maybe not see them, but if you go down to the seafloor, you might see them. And then especially off the West Coast, right off of where we were, right off Oregon, that's the system I've been working on ever since I was a postdoc. And I probably continue to work on it my whole life, because there's just so many discoveries to be made there, especially about what's happening with the microbes that are living in the methane. We've studied, there's whole groups, like Victoria Orphan's group has done amazing work on the communities that are right at that seawater interface, that are oxidizing the methane that's coming up through the seafloor. And so because I'm a glutton for punishment, wanted to figure out what was happening, 7 meters down beneath it, and actually were able to get samples from the International Ocean Drilling Program of some of the sediments that had hydrate in them. The hydrate had long since dissipated, but the DNA from the microbial cells was still in the mud, because DNA actually lasts a really long time if you keep it, if you preserve it right. And so we've been I've been studying those genomes for literally years, because it was not the answer. We were expecting, naively, I was expecting to get this beautiful signature of all these genes in the methane cycle, and it was going to make perfect sense, and they were all these novel clades were going to be making methane, and end of story, right? But in my scientific career, I tend to somehow often have my hypothesis is wrong, and so sure enough, I couldn't find any methane related genes in there. So now what we've been doing is constructing this completely different story about something I really knew very, very little about, and kind of hush about it, because we haven't. Well, really, it's because I want peer reviewers to vet for it before I put it out there, because it's really fascinating. But basically, it comes down to, how do microbes survive in essentially brines, right? In these little pockets, these little water pockets amongst the methane hydrate, which is kind of actually a pretty amazing analog for perhaps subsurface Mars or other planetary bodies, and so it's pretty exciting. Yeah. Indeed,
and one might think of methane clathrates as being this specialized topic, but they're hugely important for the climate on Earth, right? Because they contain the methane that is a very powerful greenhouse gas, and because they're contained in ice on the seafloor as the ocean goes up, those could be released. So they would have some dramatic impact on the climate, right?
And they're also being, absolutely, yes, that's true. And they're also being looked into actually by countries like Japan and Norway, who have long coastlines and don't have very much fossil fuels as potentially an energy source in the future as well. Now, speaking of controversial, that's certainly controversial, but it's in the process of happening. So.
Stay aware of methane clathrates in the news, folks, because that's a big deal. But returning to the questions, I could ask so many of them. There's a question from Marnie who asks about, apparently there's a paper that came out stating that there's possibility of life on the moon 3.5 billion years ago. What are your thoughts on life on the moon?
Oh, goodness. I should know that paper. And I will have to look at that because I don't honestly know that paper. This goes to show that I, as a professor, don't always keep up on the literature quite as well as I did as a student.
It's so much cool stuff.
But I guess potentially, I don't know. I guess this. Do you know this paper or anything about it? Is this
I have not. No, I'm not sure.
Because there's the impact that kind of created the moon.
That's way before.
And then whether life could have emerged on the moon, kind of in the hundreds, I guess, of millions of years after that. They said 3.5.
Yeah, my guess is that. Maybe it's because there's this hypothesis that during around that time period, there's a period called the late heavy bombardment on Earth. And those large meteor strikes could, throw out rocks from the Earth into the solar system. And those rocks on Earth was very much alive, 3.5 billion years ago. So maybe those rocks then impacted the moon that could potentially seed the moon. But there's just no water on the moon.
So there's fossils of,
ancient Earth life on the moon.
Ancient Earth life on the moon. Actually, I've heard that hypothesis before. Yeah. Me too. So whether that's actually growing on the moon at the time or whether it was kind of ejected and then ended up on the moon and didn't, but I'll have to check out that paper. So sorry, I can't comment more on that. But
likewise.
This is a cool study.
This is interesting. There's a question by Dr. Graham Lau. Hi, Graham, who asks, what is your favorite living thing on the Earth and why? Great question.
Oh, goodness. That's
how much time do we have?
I love the microbes, but I'm such a West Coaster. I think I'd probably have to say a tree. I'd probably say the redwoods. I'd probably say the dawn redwood because it was thought to be extinct. Right? It's this really kind of prehistoric looking. Redwood subspecies, I believe. I think the dawn redwood is my favorite. That's just what I'm coming up with off the top of my head. But I do love the microbes. I'm especially excited right now about beta proteobacteria, who really, get a bad rap, I think. But they do some really cool stuff. We're gonna, bring the make beta proteobacteria cool again or something.
There's a question, I think, that I saw briefly about the possibility that one would not have to drill into Europa to find the possibility of life. Mm-hmm. Could you tell us more about life detection on Europa?
Yes, I'll do my best. This is Brittany's habitat, but my understanding is that the Clipper, which will, when is that happening? In the not too distant
years from now.
Right, a couple years from now, is going to be able to assess whether there might be pockets actually of water in the ice so that we wouldn't have to, is that correct? So that we wouldn't have to drill all the way down, through the ice all the way to the ocean, but could actually, potentially these little pockets of water that might, like I was talking about before, these little pockets of water, could be potential habitats, right? And so maybe that's what, but they could also be, we have to be careful too, because we have to make sure whatever we're sending to Europa doesn't start growing in those little pockets, or else we'll get Earth beta proteobacteria as our answer.
Yeah, contamination is definitely an issue.
That we'll do a good job and that they won't survive the flight anyway. But, you have to do all due diligence just to make sure. Right?
Yeah, a lot of people are thinking about that problem. It's very important. And I mean, if you look at the surface of Europa, it's all cracked, and there's evidence for overturning. So the ice is not static. It's definitely moving. And we had Dr. Brittany Schmidt on Ask an Astrobiologist. I think episode 11, if I remember right, was her, and it was a wonderful conversation on life on icy moons.
Because Dr. Schmidt has a new center here called Oceans Across Space and Time. And I'm proud to be a member of that, and so they'll be doing a lot more work on that here at Georgia Tech.
Yeah, I'm involved in that too, and I'm very excited.
Yeah, and Sanjoy, of course, you are too.
So we're getting close to the hour. Oh, there's a new question. What is the Twitter handles of IceFin? I think it's just at IceFin, right? Tessa and Mike Evoy is asking that. Is that right? The Twitter handle for?
You want me to look? I can look. Multitask.
No, it's all good. We'll put it on the on the chat. Wow,
I
so
think
no,
it's just at IceFin. Yeah, it's at. Yeah. Oh no, I got it. IceFin at IceFin Robot.
At IceFin Robot.
IceFin Robot. Yeah, that's what it is. I think it has an Instagram or a Facebook too.
I think there's a nice last question here by Kavita, who asks, one is not attached to a university, but still interested in astrobiology. How can one get more information, get more involved?
Yeah, and so I would say, again, social media, because we all talk on there all the time, and it's a very inclusive community, and by all means, I mean, I ask questions all the time to the whole who is ever listening on the Twitters, and it's amazing. People will just, and sometimes I don't even know who because they don't even have you don't even have to use your real name, right? So sometimes people just come out of the woodwork and just have the most amazing questions and answers. So by all means, please be involved in, and you can go through by tagging SaganNet. You could, or is it Sagan.org? That's your handle. Yeah. That might be a good way, or to hashtag astrobiology, right? Or tag me and I'll retweet it. So I guess that's what I'd say, just the simple answer. And then from that, obviously, you can also get directed to, SaganNet or AbSciCon and AbGradCon, depending on if you are thinking about being a student or kind of associated with schools, that would be AbGradCon. So I don't know if social media is just going to be my answer mostly there, but that's the place you can get your foot in the door, right? And then kind of go from there. There's lots of opportunities of different summer schools and things as well.
And you're very active on Twitter. I know that for a fact. You tweet as at Methanogen. Jen at the end. And Jen, I know you're an extremely busy scientist. It's been clear in this conversation, and I'm so grateful that you took the time to chat with us today. It was a wonderful conversation. For those of you who are watching, make sure you keep looking at Twitter for more updates, and if you have any other questions for us, put it there. And look forward to another episode of Ask an Astrobiologist. And Jen, any last words of wisdom before we close the doors today?
I have a few banded iron formations. So I didn't get a chance to talk about these, but these are proof that there was really a lot of iron in the ocean billions of years ago. And so I'll just say goodbye with the banded iron formations. You can see how beautiful they are.
Best goodbye prop ever, everyone. I wish you all a wonderful week, month, and we'll see you next time on Ask an Astrobiologist. And until then, do stay curious. Bye-bye.